Hello and welcome to lecture number 24 in the course Advanced Robotics. In the last class, we looked at the control of a single joint, where we made the assumption, as per independent joint control scheme, that every joint is actuated by a motor, and when the motor rotates, the joint rotates. And what does dynamics have to do in this game? Dynamics essentially causes a disturbance. Okay, so which means that when the robot manipulator is moving, that there are different kind of forces which are acting. For example, inertia forces, Coriolis centrifugal forces, gravity forces, and these tend to cause or these tend to appear as a disturbance on the system. So in reality, this a single joint is a it's not a single input, single output system, but it's a multi-input. So there are two inputs. What are the inputs? One is the voltage that is being given to the motor. The second is the disturbance, which is the dynamics, which is coming on the system. Okay. So in the last class, we talked about the control of a single joint. So today, very briefly, I will go over whatever we had discussed in the last class, and then we'll move on to the next topic, that is series elastic actuators. Okay. Now, what do you mean by series elastic actuators is that you know that a joint, we are modeling the joint as there is a motor, there is a gear, and then there is a link. And we are modeling this as rigid bodies. That means there is no deflection anywhere. But in reality, you know that there is nothing like a rigid body. There will be some amount of deflection. Now, sometimes we intentionally cause the deflection, okay, or we design the linkages such that they are flexible, or we can even design the motor shafts to have some amount of stiffness. Now, why is that? Why is that done? That is essentially to develop systems which can absorb shock. For example, a robot which is running or which is walking, okay, when the leg hits the ground, what is going to happen? A lot of impact will come. So this comes as a shock to the joint. Okay, now to absorb that, what you can do, you can put a spring. Okay. Now spring is basically a kind of stiffness mechanism that we are putting at the joint. Okay, so sometimes we make the assumption of this being perfectly rigid bodies in terms of the shafts of the motors, the gears, the links. Okay, but in reality, there would be a very small amount of stiffness, because of which there will be some deflection. Now you can also intentionally introduce stiffness, and in such cases we call them series elastic actuators, where there is stiffness which is being intentionally introduced, and because of the stiffness, the robot control again has a different approach. Okay, so today we'll very briefly revise about what we had done in the last class. Then we'll look at what we call series elastic actuators. Then we'll move on to the concept of force control. Okay, so whatever we have done in the last couple of classes, we are making the assumption that the robot is moving in space, in free space. That means the robot is not constrained in any way. Okay, so the robot end effector is not making contact with anything. Okay, the moment it starts making contact, what will happen is there will be some amount of forces which are going to come from the surrounding environment onto the robot end effector. Okay, now in such cases, you may again, the robot may inadvertently hit something, which is something we don't want. But there could also be tasks where this force is required. For example, in grinding application, where the robot is holding a grinding wheel and it's using the grinding wheel on a wall. So the robot has to press the wall and move the wheel in a particular direction. Or the robot could be writing on the wall using a pen, for example. Or the robot could be pushing an object. In that case, there is these are constraint tasks in which there is interaction from the environment to the robot. And in such cases, how do you control forces? So till now, we have been talking about position control only. Okay. Now we'll talk about force control also. Now, something very interesting there is, can you control force and position together? Okay, let me give you an example. So when I'm holding this bottle of water, for example, here, my fingers are moving in free space. So this is free space position control. Okay, the moment I make contact, so my fingers are coming like this, or you can see it like this. My fingers are coming and making contact with the bottle. The moment I have made contact with the bottle, the fingers are not free to move anymore. Why? Because it is constrained now. Now I'm pressing with my fingers, I'm pressing the bottle with some force. So this is position control, free space. The moment I make contact, this is constrained motion now. Now in this case, I cannot do position control because I cannot have deflection in this direction. Okay, but I can apply a force. So can you do both together? Can you control position and force together? Okay, these are questions which we'll try and look at when we come to force control. Okay, so let's very quickly revise what we were doing in the last class. and then we'll move on to the new topic of motion with joint flexibility and force control. Okay, so we'll continue our discussion, and first I'll revise very quickly what we have done in the last couple of classes, and then what I'm going to do is I'm going to very quickly go on to series elastic actuators and then move on to force control. These are for cases where the robot manipulator is having some kind of interaction with the environment. Okay, so very briefly going through, as I was discussing, that there are in the control of a single joint, what we are seeing is that there are two inputs. One input is the desired input that we want. So this is my desired trajectory that I want. So that is one input. The other input is the disturbance which is coming from here. So this is a two input system now. Okay, and when we write our equation of dynamics, we see that our equation of dynamics comes in this form, and this is the tau that is the coming as the disturbance from there. Okay, so this is actually a two input system. Now so when we say design of a controller, what we basically mean is that this is my compensator or controller here. So it can be a PD controller or a PID controller. Okay, so basically what we are trying to see is that what should be the voltage that is going to come input to the motor that is going to get my desired output from the link. Okay, so how do we proceed? We say that we have a motor and we are giving voltage to the motor. So let us look at the motor diagram. So this is it. So I'm going to give so this is my motor. The motor is connected to the gear. Okay, and from the gear it goes to the link side. So this is my link side. Okay, now we are making the assumption here that these are rigid bodies. Okay, so these are rigid bodies, and because they are rigid bodies, we see that the stiffness K is not there. So the stiffness K, okay, so there is a J and there is friction Bm, but there is no stiffness because these are assumed to be rigid bodies. Now I'm going to give a voltage to the motor, and when I give a voltage to the motor will rotate, and when the motor rotates, the link will move and the link will achieve a desired position. Okay, so in the last class we said that when you are giving a voltage to the motor here, what happens is there is a current in the armature which is IA, and there is a back EMF which is generated because there is the motor is rotating. The motor rotor is rotating in a magnetic field, and hence there is an EMF which is generated there. Okay, so in the front direction there is a voltage V, and in the back to that there is a VB, which is the back EMF. So the total voltage in the system is V minus VB. So this is the total voltage on this armature now. Okay, and we have also seen that in terms of equation, the torque generated by the motor is equal to the motor constant into the armature current. Okay, so this is one equation. Now from this particular circuit diagram, using Kirchhoff's law, we can get so it has an inductance, it has a resistance. So L di by dt plus R into IA is equal to V minus VB. So this is the effective voltage which is on the system. Okay, and in terms of the motor, we get this. So if I take the Laplace transform of this equation and this equation, what we do get is this one. Okay, so I get this equation from a Laplace transform of the armature circuit. Now in terms of the of adding up the motor torques which are here, so we have a motor torque which is Jm into the acceleration plus damping Bm into theta m dot, which is equal to tau m. Tau m is the motor torque here, which is tau m here, minus the gear ratio divided by the link side torque, which is tau L. So on the right hand side we get this. Now we saw that the motor torque tau m is equal to Km into Ia. So I replace tau m here, and what I get is Km Ia minus tau L by R. If I take the Laplace transform of this, we get my second equation, which is this one. Okay. Now if I combine both of these two equations, what we do get is if I draw the block diagrams, our block diagram turns out like this, where we have two inputs. This is my motor voltage Vs, which is going as input, and then we have the disturbance tau L by R, which is coming as a disturbance now. And this is because of the dynamics. Now because we have two inputs, okay, what we see is that what we do is we use a superposition. By superposition we mean that because there are two inputs, at every instant we are going to assume the other input to be 0. So first we are going to find the transfer function between theta m, which is the output, to the input, which is Vs, assuming that tau L is equal to 0. So first I assume that this is equal to 0. So I get a transfer function which is this one. Then I assume that the input voltage is equal to 0. So it is basically between the disturbance torque tau L and theta m. So this is my equation 2. So the total transfer function by superposition is equal to 1 plus 2. Okay. So this is how we handle cases where there is more than one input by using the principle of superposition. Now we write our transfer functions, simplify it, and then combine this equation with this equation. Okay, so I combine this with this, and what I get is one equation here. Now you can see on the left hand side we have the inertia components, we have the damping components, and here we have I can call this K into Vt minus tau L by R. Okay, so when we say design a controller, what do we mean is that in this equation what should be the amount of voltage I'm going to give to the motor. Okay, so the controller actually decides how much voltage is going to go to the motor. Okay, so if I go back to my initial figure here, okay, so what the compensator or the controller, we can call this a controller also, is doing is it is deciding how much voltage to give to motor. So voltage to give to motor. Okay, and how is that decided? So we looked at first PD controllers, then we looked at PID controllers. So here basically we are seeing that I'm going to decide how much is going to be my V. So V is going to be, first we are saying PD, then it will be PID. Okay, so what I do is I write the equation of my PD controller. PD means proportional plus derivative, so there will be a Kp and a Kd. Okay, put it into this equation and then look at the transfer function and then look at the characteristic equation which is at the denominator and talk about stability and things like that. Okay, that is the basic flow of how we design a controller. So first we'll look at a PD controller. So my equation comes out of this form. Okay, and I'm going to decide, so what I do is I call this B effective. Okay, so I combine all of this and make it B effective. So we have Jm effective, which is the inertia. Then we have B effective, which is the damping, and on the right hand side I have I can call this K. I combine it and call it K, and we have Vk, which is the input voltage minus tau K by R. Okay, so this I'm going to make as a PD controller. So I'm going to write the equation for the PD controller, take the Laplace transform of this, put this equation in the place of Vk, and then proceed. So when I put this equation in Vk, I see that I have theta d. Okay, so we have theta d and you have theta m. So this is my theta m. This is theta ms, theta ms. Okay, so what I do is I take all the theta ms on the left hand side. So this is theta m, this is theta m, then there is theta m here, theta m here. And on the right hand side, I only have theta d. Theta d is desired position. Okay, so what comes out is in this form, theta ms is equal to k kp by omega. And omega is my, at the bottom, it is the characteristic equation, which is given by this. Now this is basically of the form, if you can, if you remember, ms squared plus ps plus k is equal to 0 in this form, and it's a second order system. So basically what we see is that j is positive, this term is positive, these are gains, they have to be positive. KKP is also positive, they cannot be negative. So M, B and K are all positive. Now in such cases we know that the poles are on the left of the j omega axis, and this is a stable system. Okay, this is something we have seen much earlier. So a PD controller always will give you a stable system. However, we also found that if you're looking at the error steady state, if you're looking at the error, then the error is at any instant is the desired minus the present position of the motor. So if I put the equations in here again, what is theta m? Theta m is equal to, this is my theta m. So if I take theta m, put it into that equation, what we do get is this equation. Now for a step reference input, okay, and a constant disturbance d by s. Please note that this is a constant disturbance. I'll just come back to this when we talk about feed forward controllers today. Okay, I'm making the assumption that this is a constant disturbance, and you know very well, because we have studied dynamics, that this is not a constant disturbance. It depends on time, because your dynamic equation itself is d into theta double dot plus h into theta theta dot plus c theta is equal to tau. Now this is acceleration, that's velocity, which means that there is time in the picture. which means it will depend on time now. Okay, so this is an assumption again we are making. Now, using the final value theorem, we can say that error steady state is equal to limit of s tending to 0, s of es, and what we get is this equation. So this is my error steady state. So this means that the error in a PD controller is never equal to 0. There will be some error. The error is going to depend on the dynamics, D, and inversely proportional to Kp, the proportional gain. So if you want less error, you increase Kp. And if you also want less error, then you operate the system slowly, such that the dynamic effects are minimum. Slowly means theta double dot and theta dot are less, are small values, are small or less. Okay. So the fundamental difference between a static system and a dynamic system is that in a static system, if the acceleration and velocities are very, very small, okay, then you can consider that to be a static system itself. Whereas if these are much higher, then we say these are dynamic systems. Okay. Now, this gives us a very, very important result that in a PD controller, your error steady state is never equal to 0, and there will always be some error, which means that if I draw this figure, which you're familiar with by now, so if I leave, it will oscillate like that and it'll come like this, and there will always be some error there, and that is my error steady state. Okay, it cannot become equal to 0 because of as we are just seeing. Now, if you want to make it 0, then you have to use a PID controller. That means with PD, you add the I, the integral component. Now, what does the integral component do? It basically integrates the error. Integrates the error means what? Numerical integration means you add the error. So if you're adding the error, it basically means that your control input is increasing. Okay. So if I'm saying PID, this is proportional derivative, this is integral. Now, if it's an integral controller, what is it doing? It is adding errors. Okay, what errors is it adding? It is adding this error. This error here, this error here is being added. So when it is integrating over time, it is adding the error as time is going on. So what is happening is the error is increasing like that. So if the error is increasing, it basically means the voltage input, because at the end of the day, it is giving a voltage to the motor, which means that the voltage input to the motor is increasing now. Okay, so ultimately it will come and join with this will come and join here. That's how a PID controller works. Okay, but we see that, okay, so this is my PID controller, and this PID controller, I put it, this is B effective. So this is K. So this part I put it there. That's my VK now. Take the Laplace transform of that. The equation, the block diagram looks like this. This is a KI branch now. Okay, so this is a PID compensator or PID controller. Okay, so from this equation, basically what we are seeing is that we can put again the same procedure. We separate the variables. On the right hand side, you'll be having theta ds, and on the left hand side, you'll have theta ms, and omega 2 comes in the denominator. This is my characteristic equation. This is omega 2 is the characteristic equation which is given by this. Now you see that this is s cubed, which means that it is not guaranteed that the roots of this equation will always be on the left hand side. If the roots are not on the left hand side always, this can become unstable. Okay, so how do we check for stability? We use the route Horowitz criteria we have seen. So we make the route table. Using this equation. Okay, and then we find that the first column, is there any sign change, a chance of a sign change, and we find that in the route Horowitz criteria, okay, for no sign change in the first column, no sign change in first column, the condition that Ki must be less than B effective plus KKD into Kp by J effective has to be satisfied. Okay, that means the integral gain has to be less than this, otherwise system will become unstable. So this means that PID control is good in the sense that it has less error, but there is a possibility that it will become unstable, okay, if you don't satisfy this condition. So you have to be very careful while tuning the PID controller. Now in the when we are just discussing this, I just briefly mentioned that when we are finding the error steady state, I made the assumption that this is a constant disturbance. And in reality, this is not a constant disturbance. That means it is going to keep changing. This D will change. So one way that we could have a better controller is, suppose I can compute the dynamic model here. Now look at this. I have the dynamic model. This is my servo part of the control. This is my controller, basically KP and KV. This is PD controller, which is here. So this is my servo loop. This is the robot arm. Now suppose I can compute the dynamic model and feed it forward. Okay, then I have the information of how much disturbance torque is coming. Okay, so I can compensate it very, very easily. So the controller can actually compensate this disturbance that is coming. In the previous case, we did not know what was the disturbance. But here, suppose I can accurately compute. In the previous case, we made the assumption that this is a constant disturbance. Now I'm saying that if I compute the dynamic model and I know how much disturbance is coming at every instant, then I can include it in my control structure. And that is this. This is also called feed-forward control. But there is a little problem with this. One of the problems is that the time to compute the dynamics. That we have seen that you have to find the position, velocity, acceleration when it is moving. Then you have to compute it in real time. And computing that in real time is not possible. Okay, it takes a bit of time. So what will happen, your controller is going to, this loop is going to get slightly delayed. Okay. Then, well, with a fast processor, maybe this can be done almost real time. You can compute it very, very fast. But the second problem that comes is inaccurate dynamics. For example, when we are saying our equation is D, or we talk about M into theta double dot plus H into plus C theta is equal to tau. This is my inertia terms. Now the inertia matrix or the inertia tensor basically contains the link. So it has link. Now on the link we know there are gears, then there is a motor, then there are wires, there are encoders. Okay, all these are there. Now you cannot exactly find out or very accurately find out the inertia of all this because they are inside. You don't have access to them. The manufacturer also doesn't tell. So there is inaccuracy in the dynamic computation itself because the gear inertias, link, wires, these are not known accurately. So if these are not accurate, that means if this term is not accurate, then even if you can compute the dynamics in real time, your answer is not very accurate because this equation will not give you an accurate answer. Okay. The third is discrete time control. As I was saying, that it takes time to control. So there is some error which will be involved and it is discrete time. You cannot do it in continuous time. It's infinite. Okay. So you have to compute this at in particular instance of time. Okay. What I mean is if the link is moving from here to here, it's moving from there to there. I compute this at particular instance of time. So it is discrete time. I cannot compute it at every instant because it is infinite. So the third problem that comes up is discrete time control. So these type of controllers are called feed-forward control. And feed-forward control, for example, if you are controlling one link or two links, then probably it's a good use. It's a good thing to do because computing for one link is easy, and you're getting a very good dynamic model, and you're having a good dynamic. The disturbance is being modeled very accurately, so you'll get a better controller. But if you do for 6 degrees of freedom or 10 degrees of freedom, where your dynamics itself is not very accurate, it doesn't help much. Okay, but this is what we call by feed-forward control. As the name indicates, we are giving a feed-forward of the dynamics. So this is my control equation in feed-forward control. So this is the dynamics now, which I'm computing. And this is coming as a feed-forward term. This is my HS and GS as per before. So if I take the transfer function, what we get is, this is my total transfer function. And these are assuming that GS is equal to QS by PS. Okay, so this is my, this is PS, this is QS. Similarly, I'm making this assumption, and then this is my transfer function. Okay, what am I doing? I'm computing the dynamics and I'm giving it forward in that control equation. Now, if you choose the feed-forward transfer function such that it is equal to 1 by GS dash, then the inverse of the plant is given by this, and the error becomes equal to this, and we can show that the error becomes equal to 0. Okay, so in this particular case with the feed-forward controller, although there are two inputs, one input here, another input there, because we are able to compute the dynamics accurately here, I can take care of this disturbance that is coming. I hope you understand and realize this point, that if you can estimate the disturbance, you can cancel it. Okay, so what this FS term is doing, the feed forward term, it is computing the dynamics and then actually taking care of this DS disturbance that is coming from there. And because of which, even for a PD controller, what we are getting is that your error steady state is equal to 0. Okay, so this is another way of controlling a robot manipulator. Now, in whatever we have done so far, we have made the assumption that the links are rigid, the shafts which are in the motor. So the rotor of the motor is connected to the gear by a shaft. The output of the gears are again a shaft which is connected to the gears on the link side, and then from the gears again. So these are shafts. Okay, and this is my gear, and this is a shaft again here. So we made the assumption that all of this are rigid bodies. Okay, that is one. Now in reality they will not be rigid bodies, so there will be some amount of stiffness there. Okay, so in a shaft, if I draw it here and I give a torque like that tau, there is going to be some deflection in terms of del theta, very small amount. Okay, that is what I mean by the stiffness of the shaft. It's like a spring. You can have a linear spring or you can have a torsion spring. In a torsion spring, for example, I have a torsion spring like this and I rotate it. Okay, I apply a moment. What will happen is it is going to deflect by a small amount del theta. Okay, so tau is equal to k into del theta. Okay, this is my stiffness k. Okay, now the shaft will have some amount of stiffness. That means it will have a k value. Okay, so it can be small or it can be large. Now if you want to intentionally put stiffness, for example, I gave the example that when you have a walking robot, which we'll be considering as we go along in the next few classes, when the walking robot is walking, so this is the one step, and in the next step what happens is this foot goes forward and hits the ground there. So when this leg goes forward and hits the ground, there is an impact there. Okay, so there's an impact which is happening. So it is walking and the walking robot is moving forward. So it is based on this leg has moved here and the other leg has come there now. Okay, so this is the other leg. So the leg has come there now and it's hitting the ground here. Okay, so this basically means that there is some amount of impact which is coming. Now if there is impact which is coming, the impact will get transmitted backwards into the joint now. So the impact which is coming on this side, the link side, will get transmitted onto the gear and the gears will have impact, and that can damage the gear or there will be a shock on the system. Okay, which is not good. Now that is one aspect of it. The second aspect of it is when we talk about safety. Okay, say for example I have I have a link like this and it's moving and there is a wall. This goes and hits that. That means there is a force which is coming onto the end effector now. Okay, again the same thing, there's an impact, there's a force which is coming, it will get transmitted onto the joint. Okay, and can damage the joint. Now suppose I have a mechanism of absorbing the shock, like, or the force which is coming. What can I do? I can put a spring there, or I can make the link itself compliant, flexible, such that if it hits, what will happen? The link will bend like that. I hope you can imagine. Okay, or this link will bend. So it's a shaft. If I give a force there, what will happen? It will just bend. Okay, so it is like absorbing this force. Okay, so this is in the case of a link flexibility. I can also put a torsion spring at the joint, and that is a joint stiffness which I'm introducing in there. Now for robot safety, very often this is done. Okay, intentionally stiffness is introduced such that the joint becomes the joint can absorb some amount of shock. So what does it look like? So from here, this is the ideal case. I come here, and what we are seeing is that here we do have a motor. So this is my motor side, but the motor shaft is connected to a torsion spring. Okay, so there's a torsion spring and then it is connected to the link. So compare this figure with compare the figure at the top and the figure at the bottom. Here it is directly connected. Here there's a torsion spring. Okay, so now you can imagine that the motor is going to produce some torque tau. Now because of this torque tau m being produced by the motor, the spring will have its own k. So tau m is equal to k into del theta. Okay, so what is going to happen is the spring is going to first deflect, and for that very small deflection there will be no change on the link because the spring will deflect, and then the link is going to change its position. So now if I say here, if I just give an example, that if I say my gear ratio is 1:1 and this rotates by 20 degrees, the motor rotates by 20 degrees, gear ratio 1:1, the link will also rotate by 20 degrees because it is a 1:1 coupling. In this case, if this rotates by 20 degrees, okay, the link need not rotate by 20 degrees, it could rotate by 18 degrees. That will depend on the k here and how much deflection is there in the spring. I hope you understand that. So now if that's one way. When I'm rotating on this side, the link will rotate less. Now on the other side, if I give a force there, what will happen? The force need not get transmitted onto the motor. There will be some deflection on the spring now. Okay, so this is the meaning of adding stiffness to the joint. Sometimes it is intentionally done to absorb shock to make the robot safe. This is called drivetrain dynamics, and it is sometimes also called series elastic actuators. Why series elastic actuators? Because it is added in series to the motor. Okay, that's the reason why it's called series elastic actuators. So this is an actuator which is a motor, but the output of the motor is connected to a series spring, torsion spring in series, and then it goes to the link side. Okay, now we need to understand very carefully the meaning of stiffness here. Okay, so let me just play this very small video which will give us an idea of what is stiffness and what it means. So by changing k, so please listen to this carefully, that when we change k, we can make it behave in a different way. Okay, behave differently. Okay, what does it mean? We are looking at this next video, and we see that what it basically means. So here we are seeing that okay, let us look at how do we design this variable stiffness actuator when there is a stiffness at the joint. Okay, then we'll come back to the video a little later probably. Okay, so here we have a system in which we have a motor at one end. So this is my motor, and we have the link on the other side, and we have a spring which is here. Okay, now please note that this is a passive spring. What is the meaning of this word passive spring? It basically means that if you have a spring, let's look at this example here. So I have a spring like this. This is a linear spring. I give a force F. This one end is fixed, and it deflects by a small amount del x. Now F is equal to K into del x. Okay, which means that for a fixed K, this del x is also fixed. That means it's passive system. You cannot control the del x for a given K. Okay, so suppose I give 10 newtons here, and K is, if this is 10 newtons and K is equal to 1, then your del x is equal to 10. Okay, so you cannot have force of 10 newtons where K is 1 and say I want del x equal to 100. That's not possible. Okay, so this is basically a passive spring, which means that because this is a passive spring, so you cannot actually control the amount of stiffness which is occurring. Okay, so we are looking at a system in which I'm going to give an input to the motor. Okay, the motor will rotate. Now when the motor rotates, first the spring is going to deflect. Okay, so let me there will be a spring deflection, and after the spring deflection the link is going to move. Okay, one of these equations is a passive equation, which is this one. Okay, so now let's look at this equation. We have two equations. One equation is from the link side. So this from the link side, this is from the link side. So link inertia into acceleration, where theta L is the, so this is my theta L is link side, theta M is the motor side angles. So theta L double dot is the acceleration of the link, plus damping into the angular velocity, plus K into theta L minus theta M. So what is the effective deflection here? So if this is my theta L, that's my theta M, then in between there is a theta L minus theta M, right? And that is my K into K. K is the stiffness. That is this equation here. So here in this equation, force or tau is equal to theta L minus theta M, which is actually equal to the deflection, and into K. Okay, that is what I'm writing here. So this is from the link side, which is equal to 0. Now equal to 0 means this is passive, there is no input on that side, and hence it is not controlled, right? Now if you're looking from the motor side, when the motor rotates, it's motor inertia into acceleration plus damping into velocity minus k into theta L minus theta m is equal to u. This is my motor input. Okay, so this is my motor input. So when you're giving the voltage to the motor, you're giving an input to the motor. The moment you're giving an input to the motor, what is happening is some of that is causing the deflection here in the spring, and the other part of it is going to change the position of the link. Okay, now this, you cannot control this part exactly because K is passive. Okay, or K is fixed for a particular spring. Now when I draw the block diagram, what we get is this one. Okay, this is my block diagram. So what we can do is I take my first equation. Okay, here there are two equations. So there are two PMS from the motor side and PLS from the link side. Okay, so PLS into theta LS is equal to Km into Km. So from this equation, I put theta L, all the theta L's on the left hand side. After taking the Laplace transform, I take the Laplace transform, theta L's in the left hand side and theta M on the right hand side on this equation. So on the right hand side, there's only one theta M, that is this one. So PLS into theta LS is equal to K into theta MS. And what is PLS? PLS is equal to this stuff. So this is equal to theta LS, right? Okay. So that is one. The second is here again. I have theta M and theta M and theta L. So I take all the theta M's on the left hand side. And on the right hand side, what do I have? I have on the right hand side, I have theta L plus there is a U. So I get this K into theta LS plus US. Okay. So here I have one from this equation and one from this equation, which is this is from equation 1, this from equation 2 after taking the Laplace transform. Okay. And in terms of block diagram, they look like this. So when I give an input U, let's try and understand the block diagram first. So when I give an input U to the motor, I'm giving voltage to the motor. What is happening? It is getting multiplied. Let me clear this a bit. So when I'm giving an input U, it is getting multiplied into 1 by PMS. Okay, so this PMS is here. So this will become 1 by PMS will come here. And the output is going to be my theta MS. Okay, so what will happen is my input is here, output is theta MS from this equation, right? And this theta MS is going to go from here. Theta MS is being generated, then it's going on that side, okay, which is going through the spring, which is K into 1 by PLS. PLS is this side. Okay, so this is my PLS. Okay, so this is on this equation. So it is K by PLS. So theta L is equal to theta M. Now, let me clearly write it. So from here, I get theta L is equal to K into theta M divided by PLS. From this equation, this is what I write. So input is my theta MS, which is here, is getting multiplied into K and is getting divided by PLS, which is here. And the output is my theta L, which is this one. So I'm using this equation and this equation to make my control loop diagram. And it is closed loop control, so the K, it is coming back this way now. So if I find the transfer function here, okay, how do I find the transfer function of this? Let me come here. How do I find the transfer function? I multiply this into this. This is in the same loop. And then if this is my GS, that's my HS. That's HS. So transfer function is equal to GS by 1 plus GSHS. Okay, so transfer function will be equal to GS by 1 plus GSHS. Right? So this is my characteristic equation. Okay, so what we are doing is I'm closing the loop, multiplying this into this, and then it comes out like this. So theta L by US, this is my transfer function. The characteristic equation is this fellow. So the stability of the system will depend on the roots of that equation. Now please note that PL, it is PL into PM. Now if you just go back and see PL and so PL is S squared, PM is S squared. So PL into PM becomes S raised to 4. So we are getting S raised to 4. Okay. So it's just a question of multiplying this into that. okay, PL into PM. Okay, so what we get is this equation. Now this equation has s raised to 4 now. Okay, so we are not sure where the roots are. As far as it is s squared, it is fine. They are going to be on the negative side of your j omega axis. But the moment it becomes positive, it becomes s raised to 3 or s raised to 4 that we are seeing. In the case of PID controller, we saw it was s raised to 3. Here we are seeing is s raised to 4. So now we need to see if is there anything else we can figure out from here. Now what we can do is that we can say that BL and BM are neglected. So BL is equal to BM is damping, which is very small. So BM and BL I cancel from here. BM, BL is cancelled. So BL is cancelled, BM is cancelled. And if I do that, what we are left with is only this term. So I'm only left with this term and this term. Okay, JL JM s squared plus K into, so this means that this is an s squared. So I can take s squared common. What I'll be left with JM, JL JM s raised to 2 plus Km into JL plus JM. Okay, this is what we are left with, right? Now this means if I equate this to 0 now, it basically means that you have a double pole at the origin. So s squared is equal to 0 means you have two roots at 0. Okay, so we have a double pole at origin and we have a pair of complex conjugates. So from the remaining term, JL JM s squared plus K into JL plus JM is equal to 0. So if I put that, what will happen is s squared will become equal to JL plus JM, okay, divided by JL JM, which is shown here, and it is K by 1 by JL plus 1 by KM by JL. Okay. And this basically gives us a root, a pair of complex conjugate poles at J omega. Now because it is minus, you're seeing that this fellow, when it goes on the right hand side, it will become minus. Okay, so this will become minus. Okay, when it goes on the right hand side, so s squared will become minus. So it basically means that you have two poles at 0. So s squared is at 0 and the other s squared is complex conjugate poles. So this is a stable system, okay, because all the roots are on the negative of the j omega axis. Now this is the system. That means we have not added a controller till now. Now I want to control this system by putting a controller. Okay, so basically I now need to put a controller here. So how much voltage I'm going to give to this motor will be decided by the controller now. Okay, so the controller can be PD, can be PID. Okay, so now I'm adding a PD or a PID controller to determine how much voltage should be given to the motor such that the link will go to some desired position. Okay, now as far as the system is considered, this is the system and the system is stable. Okay, we are seeing that although it is s raised to 4, all the roots are on the left of the j omega axis and there are 2 of them at the origin. Okay, but they are stable. Now I'm putting a PD controller first. Okay, so this is my PD controller that I'm putting, and in the PD controller basically it is Kp plus Kd into S. So if I take Kd common, I can write it as S plus A for different values of A. What is A equal to? A is equal to Kp by Kd. Why am I doing this? Because there are two variables, right? So Kp and Kd both are variables. Okay, so to reduce it, I'm reducing it to Kd into S plus A, and for different values of A, I can see what happens to Kd, and then I can keep varying Kd and see what happens. Okay, so for example, I can put A equal to 1, put different values of Kd and see how it is behaving. Okay, so now my block diagram comes out like this, where we have a 1 by PMS, 1 by PL. Okay, so this is the earlier part. This is my compensator, this is my controller. Okay, so my input is coming here to the controller and then it's controlling the plant. This part is same as before. Now we are having a feedback, right? So because in the Kp and the Kd, it is theta d minus theta m into Kp. This is something we have seen. Okay, plus we have the Kd into S, right? Plus we have a Kd into S. Right? Now basically what we are saying here is that I need a feedback which is this one. Now if I want this feedback, no, I cannot write it like this. I need this feedback. I cannot write it this way. So when I want the feedback, okay, this is my feedback which is coming from here. This is my feedback which is coming theta d minus theta m. Okay, theta ds into theta ms. Okay, so for this feedback, the feedback can be taken either from the motor end. Okay, that means here is my motor, this is my motor, and this is my link. Okay, so I can take the feedback from the motor side, so which basically means, let's come back here again. So I'm taking my feedback from the motor side. This is my motor side. So when the motor is rotating, I'm taking feedback from here. That means I'm trying to control the motor rotation. Or I can take the feedback from the link side. That is my feedback encoder. If I say I have an encoder there, I can put my encoder here, or I can put my encoder there now. Now in the previous case, in this case, I mean, if I put my encoder here, or if I put my encoder there, and I know the gear ratio, then both of them are same, because I know the gear ratio, right? Whereas in this case, there is a spring in between. So what is going to happen? The encoder readings are going to be different. Okay, you understand that, I'm sure. That because there is a spring in between now, the encoder's feedback is going to be different depending on where you put your encoder. So in the first case, I have put my encoder from the motor side. So just behind the motor, I have put my encoder, and I'm getting my feedback from here. Okay. Now in such a case, what we see is that if I draw the root locus, so if I draw my root locus of the system. Now what is the root locus of the system? The root locus of the system means that in the PD controller, you can vary your KD and your KP. You have two gains, you can vary them. But for all values of KP and KD, can you plot where the roots of the system are? Okay, so for different values of KP and KD, you need to find where the roots of the system are going to be. Okay. And how do we do that? One way is that for different values of A, I can vary this KD, and I can see where the roots are going. Okay. And if you do that, the locus of that is basically called the root locus. Okay. That means for all values of KP and KD, what are all the possible places of the roots of the system will give you the root locus. And what is the point of doing this, or what is the advantage of doing this? The advantage of doing that is, if the root locus is on the left side of your j omega axis, this is my j omega axis, then that means irrespective of what values of KP and KD you put, your roots are always on the left of your j omega axis, so it's a stable system. Okay, so stability is guaranteed. So in this particular case, you can look at the root locus of this system. Which system? Where the encoder feedback is from the motor side. This is called motor angle feedback. So I'm putting my encoder. I have put my encoder here. So I'm putting my encoder here. So this is my encoder here. And my feedback is going from here. So this is theta m. Okay. I don't worry about theta L now. Okay. So my feedback is going from theta m, and I'm controlling theta m only. Now, if you're doing that, then what we find is that when I'm using a PD controller and I draw the root locus, I see that all the roots are on the left of the j omega axis. This means that this is a stable system. Okay. So if you're taking motor angle feedback, the system is stable. It cannot become unstable. Okay. Now, the other option is I take the feedback from the link side. So let's go back to the figure again and see what this means. So now I remove my encoder from here. Okay. So I put my encoder here now. On the link side, I put my encoder here. Okay. So my feedback is coming theta L from this side now. That's my feedback to the control system. Okay. In that case, the control block diagram becomes like this. This is my link angle feedback. So it's going from here into there. Okay, that's my feedback. Theta L is the feedback. In the previous case, theta M was there. It was like this. Okay. Now in this case, again, we need to look at the stability. How do we do that? I have to close this loop diagram. So I multiply this into this. Then this is my GS. That's HS. So I multiply GS, HS, and then multiply with this one. Okay, so first I multiply this into this, then I find GS1 plus GSHS Okay, this is my transfer function, and then multiply it with this loop now. So I'm going to get one overall transfer function. Then I look at the characteristic equation of that transfer function. Okay, and again we see that there is a kp plus kd into s. Okay, so what we do is we have to draw the root locus, and to draw the root locus, we draw the root locus, and what we do find is that the root locus looks something like this. So this is my root locus, and it looks something like this. So this is my j omega axis. So this will basically mean that this root locus shows that for very large values of kd, the roots are actually going like that. So it is crossing over here, which this means that this is my stable and this is unstable region. Okay, so this is basically showing us that if you're taking your feedback from the feedback from link side gives an unstable system. From the link side may result in an unstable system, may be unstable. Okay, so this is very important. So when we are using series elastic actuators, we should be very careful which side we are taking the feedback from, because if you're taking it from the link side, okay, you may end up making the system unstable, depending on if you're putting very high values of kd. Okay, so this was basically to explain that when we are having stiffness, we are adding stiffness onto the joint. The advantage of putting stiffness is that we can absorb some of the shock. Okay, and very often in a lot of robots these days we are using what we call series elastic actuators, and this is the basic control structure of a series elastic actuator. And in terms of control, there is a problem or difficulty is that this K is not controllable. You cannot control that K. It's a passive system. Okay, so it's like I was explaining here that whatever force you give, the deflection that will happen, that you cannot control. That is a property of the system itself. Okay, so and the additional problem that if you're taking motor angle feedback, then there's a chance of the system becoming unstable. Okay, so today we looked at first we looked at control of a single joint. Then we looked at series elastic actuators, where we are trying to control, we are trying to introduce stability, we are trying to introduce stiffness in a joint, and then we are trying to control the motor such that I get a desired position on the other side. And as I was saying, when we come to biped locomotion, or mainly biped locomotion, we'll see that these kind of actuators are used these days, essentially because we need to control, we need to absorb the kind of impact that is coming. Okay, so far what we have been discussing are unconstrained tasks, which means I have a manipulator like this, and this manipulator is moving around in space and doing a particular task. Maybe it's picking up an object and keeping it here. Okay, now this is moving in free space, so there is no forces being applied anywhere on the system. Now suppose we have a manipulator which is doing grinding application. This is a grinding wheel, and it is doing grinding on this surface. So the wheel is rotating, and the manipulator has to apply a force on that direction because you're doing grinding, and you have to move the wheel in this direction. So that's position. So this is the velocity, and that's a force, and they are orthogonal to each other. So here this is a case of a constrained task. Okay, so this is what we call by a constrained task, where the robot is not constrained in what direction. Constrained means not free to move in a particular direction. Okay, that is the meaning of a constrained task. So today we talked about, first we talked about control of a single joint. I just revised what we did in the last class. Then I talked about control of a joint which has stiffness in the joint, for example, series elastic actuators. And we saw that it's very important to understand that depending on which side you're taking your feedback from, either from the link side or from the motor side, the system can become unstable. Okay, so this is something we have to be very careful of when we are introducing stability in the system, when we are introducing stiffness in the system, okay, in terms of stability of the system. So we'll stop here today, and then we'll move on to force control in the next class. Thank you.